All right, so like I said, the gateway test, 10 questions. You find the derivative, you've got to get 8 right. Now, the plan is, typically we do it one time in class, and then after that you have to do it outside of class. That's a little harder with our schedule and so forth. That coming outside class have to be in the morning. Typically it doesn't take too long. Typically people could do them in a half an hour or so, probably. So before school, it could be after school if you've got a 4 o'clock off, or a block off, possibly. I guess it'd be 4 o'clock probably. To get it passed, and probably need to get it done before Christmas. Although if it takes you 4 or 5 times, it might be harder. You can only do one a day. But leaving it till after Christmas and trying to come back is kind of tough to do. So typically people get passed on 3rd or 4th attempt. Those people that study and try and keep at it, whatever. Okay, I did say that there's, if you take it twice and your best score is a 6 out of 10, and you just don't come back to retake it, or I just assume that you want to take a 6 out of 10 with 60%. So out of 30, it's a 30-point quiz grade. So that'd be 18 out of 30, right? That's what we go with the grade book. But it's based on how many attempts. So one attempt, 1 attempt successful, 30 out of 30. 2 more attempts, if you're successful on either one of your 2nd or 3rd attempt, it's 27 out of 30, which is a 90%. Okay? If you're successful on one of your next 2 attempts, it's a 24 out of 30, which is an 8. Okay? And if you're successful on one of the next 2 attempts, it just keeps going down. So 21. And of course, by then it's a 70. And by then you may be by, what is that, 7 attempts? By then you probably have gotten a 7 out of 10, or you maybe have given up on it. I don't know. Hopefully nobody in here is in that boat. Okay? So that's kind of how it works. All right? So basically, we've introduced some of these derivative rules. You have this homework last night with the IXLs and stuff to just, what are the basic rules for exponentials, for logs, for trig functions, at least for sine and cosine, and then for just your power rules. Right, and that encompasses most of the basic functions. And so now what we got to do is something like this. What happens now when we take these basic functions and we combine them in different ways? Now we already know if we add basic functions together, we just do each derivative. So if you got x squared plus sine x, instead of times, if you got x squared plus sine x, the derivative is what? 2x plus cosine x, right? If it's plus or minus and you string together some functions, then you just do each one of their individual derivatives and string them together with plus and minus. Okay, so we have that rule. And then we have the rule, if you got a number on the inside, you kick it out. If you got numbers multiplied on the outside, it just hangs out there while you do the derivative. So we have some of those rules already. Okay, so now we just got to put together the rest. And then we have a few functions we haven't talked about. The rest of the trig functions. We haven't talked about the inverse trig functions like arc sine and arc cosine, so we got rules for those. But that's about it. Okay, and there's another type of differentiation or derivative process that we have for special types of equations that we'll get in there in the next day or so. But other than that, then we'll have some practice time. So my guess is this gateway test would be probably Monday or Tuesday of next week. Is kind of what I'm guessing where that'll be. So I'll give you the rest of that week, and then 3 or 4 days of the next week to get through that. Okay, but it's best to pass it the first time, right? Because then we're going to go on and we're going to do some stuff in chapter 4 for a few days leading up before Christmas break. So we're moving on to that. So then you got to be kind of doing both, kind of getting ready for the gateway test and keeping up with the other stuff. So it's best to work really hard this week in practicing these things. I'm going to give you some websites you can go to practice. There's some more IXLs and that kind of stuff where you can practice some as well. And so really how much time you put into it is going to determine. Okay, so here's the dilemma, right? We'd like for this to be 2x cosine x right here, right? However, and this is where we're going to let Braylon help us out here. So Is that yours there? Okay, so go onto your calculator screen, Braylon, and let's go to the derivative. And now, obviously, this quiz is no calculator, right? Sorry. So we're going to go ahead and put in x squared, but remember, the calculator can be kind of a check, a way for you to check your answer, and I think I showed you earlier. Now, don't hit enter yet, Braylon. So go ahead and do x squared times sine x. But the calculator can certainly be a way for you to check your answers. Remember, they're probably not going to look the same as what you get always, and so you can take your answer and their answer, hit equals, and see if you get, see if it comes and says true, right? So we're wishing this would be 2x cosine x, but as it turns out, we've actually shown already it's not going to be. Go ahead and hit enter. Yeah, it's kind of hanging up. All right, there it comes. All right, now let's look at that. What did it do? Now, I will tell you that when we do it, we'll probably switch those around. There's a plus sign, but when we do it, we'll probably switch those around. So what's it look like it did? I mean, I see a cosine, I see a 2x in there.
So this is the prime of the first one, and then just the function.
Kind of took turns, didn't it? Looks like it took turns. That's how I would describe that, right? It said, okay, we'll do the derivative of the first one. They say, again, I think we will write it with this one first. But the calculator does it kind of highest power, so it did that. But to me, it would be like, well, it did the derivative of that one and then just left that one alone, right? And so it did 2x and then tacked on the sine x. And then it did the other one. Then it left the x squared alone, and then it did the derivative of sine, which is cosine. That's exactly right. Okay, that's exactly what it did. And so if we come back to here, so the derivative of that, the way we would normally write it, is we would go 2x sine x plus x squared cosine x, right? So now let's write that as a rule, and that is going to be known as our product rule. Our product rule, okay? So the product rule is, as it sounds like, when you're multiplying two things, you're going to do the derivative of the first, so you're going to do f prime of x. You're going to leave g of x alone. Then you're going to add, and then you're going to leave f alone, and you're going to times by g prime. Now the order doesn't matter because it's a plus sign, and then the f prime and the g are multiplied, so you could flip those around if you wanted to, but just to keep everything in order, we do that. Now here's how it's normally written. Now this is going to be our first introduction today to using u and v to represent our functions, but it just allows us to eliminate some of the extraneous stuff there. I mean, do I really need those x's in there in every one of those? I mean, I understand that f is a function of x and g is a function of x, but for whatever reason, it just gets weird, right? F prime g and stuff like that. So the tradition has been for years and years through many textbooks to use u and v. So think of it as u of x and think of it as v of x, right? But when we see u and v, we just understand those are functions of x, okay? So it's like u equals, in this case, x squared, v equals sine x, right? So because notice, it still says with respect to x down here, right? So u and v just stand for some x's. All right, and so it's going to be u prime v plus uv prime. And that just rolls off the tongue a little easier to remember maybe. And again, the order doesn't matter, but I like writing it in this order because of the rule we're going to see next. And the order does matter. And so then we can just be the same on both. So, product rule, u prime v plus uv prime. We take turns. That's the product rule. Okay? All right. So, let's just practice one here real quick. So, if I have x plus 4 to the 5th times sine 3x, I'm not going to want to FOIL out that x plus 4 to the 5th. That'd be a royal pain. I don't have to do it. We already have some rules for that. But what it is one function multiplied times another function. So it's like here's your u and here's your v, right? So what does the product rule say to do? U prime and then v, right? So do the derivative of the first, so that would be 5. We leave the inside alone. That's always what we do. We drop that down to a 4. Do we have to kick out anything there? Kick out anything? No. And then what do we do with the sine 3x? Just tack it on, right? When I say tack it on, I usually mean multiply. I don't know why I say tack it on, but it means it's not a very mathematical term, but it just means multiply. So do the derivative of the first. We leave the second one alone. Plus, then we leave the first one alone. And then we do the derivative of the second. Now, what do we get when we do derivative of sine 3x? 3, because we've learned that we have to kick out that 3, so now we're going to have 3 cosine 3x. Now, I would prefer the 3 to come around in front here, and then it'll be cosine 3x. Now, the first time you do it, you might have done it and stuck the 3 at the end. That's fine. You can stick the 3 on the end. That's fine, and I don't care. You can even leave it there. Now, one of the things we'll talk about before the gateway test is how do you want the final answer written? How much simplifying is enough? Well, what I'm going to tell you is the obvious simplifying you need to do. Now, the problem with obvious is what's obvious to me might not be obvious to you. So over the course of the next 3 or 4 days, we're going to try to get on the same page as to what is obvious, simplifying, okay? Because if you're going to get a 30 out of 30, you're going to earn it, right? So if you miss one little thing, right, if one little thing is off, it's wrong, right? It's wrong. Now, you still can miss 2. You can miss 2 and still get a 30 out of 30, right? So what I would say is if there had been a 4 in front of this sign, right? If there had been a 4 in front of this sign and then you kick out the 3, you better put the 4 times the 3 and make 12. You don't leave the 4 and the 3 separate. You need to put those together and multiply. Okay? Now you need to think of this as a group of terms, and this is a group. Well, this is one term, this is another term. So anything that's multiplied in here can be put together. Anything that's multiplied in this group can be put together here, okay? But that would be your final answer right there. There's nothing else you have to do. Some people say, well, you can factor out an x plus 4 to the 4th. Each one has an x plus 4. Now, the only time we ever factor anything is if we can then cancel. Factor something and then cancel is fine. If you do a derivative that's 3x plus 6 over 7, and you say, oh, I can take a 3 out of the top, don't bother. Why take a 3 out of the top, right? The only good taking a 3 out of the top does is if you can then cancel it with something on the bottom. So if this would have been a 6 on the bottom, then by all means take out a 3. But it's not, so just leave it. Just, you might say, well, I'll split it apart. Well, true, you can split it apart, but why bother, right? It doesn't really simplify it. So those are some of the things you think about when you're thinking about simplifying. Okay, now let's look at this one. So now instead of x squared times sine x, let's say we had x squared divided by sine x. So Braylon, type this in to your calculator. Again, it'd be nice if this was 2x over cosine, but it's not. Okay, we can't just do their individual derivatives when we're doing a division. So we go to our trusty calculator and look at it. Now, the calculator has done some weird stuff here. The calculator has pulled out an x, which I think there's no call for. There's no reason for doing it. So let's see what it actually has instead. So I'm going to distribute this, and I'm going to flip around the order they wrote it. So I'm going to take this negative x times this one over here, and that would be a positive 2x sine x. And then I'm going to do this first one. That would be negative x squared cosine x all over sine of x squared. That's how we would write it, okay? So let's look at my answer and let's see what they have done, okay? Well, what's the top look like? What's the top look like? Doesn't it look like the product rule we just did? Didn't they take turns again? Okay, they took turns. They did the derivative of the top, 2x. They left the bottom alone. Then they left the top alone. And then they did the derivative of the bottom. Except this time they did what? There's a subtract sign in there. Okay? There's a subtract sign. And then what did they put on the bottom? just the bottom square. Okay? So it's the same as the product rule, but the order matters because of the subtract. And then they put the bottom square. Okay? That is called, so if we come back to this, the answer was 2x, derivative of the top, the bottom left alone, minus the top left alone, times the derivative of the bottom, which is cosine, all over the bottom square. Now, notice how I wrote it sine x quantity squared. Can we use the lazy writing? Sure, we can go sine squared x like that, that's fine. But remember what that means. That means sine of x times sine of x squared. Okay? There is no simplifying to do there. Sure, the calculator took out an x, but what did it do with it? Nothing. You can take out an x, but there's nothing here. But if you could, let's say you could take out a sine. Doesn't happen very often, but let's say you could take out a sine. Then you would want to, because then you can cancel it with one of the signs on the bottom. That's the kind of simplifying you're looking for. That's what I would call the obvious simplifying. But taking out an x on the top doesn't do us any good. Okay? Now, when that usually happens is when you get an e to the x. Because think about an e to the x. E to the x is its own derivative. So when you do the derivative of e to the x, you'll get an e to the x here. And then when you leave it alone on this one, when you take turns, you leave it alone, you get another e to the x. So oftentimes you can take out an e to the x, and maybe there's an e to the x that'll cancel. So that's something you'd be on the lookout for. Okay, so this is called the quotient rule. So if you have two functions that are divided, we do the derivative of the top and the bottom left alone minus the top left alone times the derivative of the bottom all over the bottom square. Okay, but again, that's a whole lot of x's to deal with. So the way we usually write the quotient rule is if we have u over v, which is just two functions, u function on top, a v function on the bottom, we're dividing, then it's going to be the top, so it's u prime v minus uv prime. So this is what I was talking about. This is why I like remembering the product rule this way, because the quotient rule is the same order, but the order matters on the quotient rule because of the minus sign. That minus sign gets us in more trouble because of having to distribute it through and so forth, just like the definition of the derivative. And then that's all over v squared. Okay? And if you want to, I hesitate to even throw this in here, but this is what my high school teacher taught us. High over ho. High is up high and the ho is down low. And the derivative of that is, and he had to rearrange it a little bit, it's the bottom left alone times the derivative of the top minus the top left alone times the derivative of the bottom all over the bottom square. That's how I look. Ho-de high minus high-de ho over ho-ho. So I throw it out there. But if you want to remember it that way, you can. But that is, he was kind of funny that way. Okay? But probably just going to think of it this way. Right? So the product rule is u prime v plus uv prime, and the quotient rule is u prime v minus uv prime over v squared is the quotient rule. Okay? You just follow that and then possibly simplify. Okay, let's look at a couple of examples here of some different things you're going to have in your homework. Then I'm going to give you about a half-hour work time here. All right, so there's going to be just some basic problems like the ones we just talked about. Okay, there's going to be one like this, right? There'll be one like this, something like this. Just basic, follow the rule. Okay, check your answers, kind of thing. Okay. All right, but then what kind of weird or different or other kind of questions could they ask you where you think about this? Well, they might do this. They might say, well, here's h of x. H of x is equal to f times g. We don't know what those functions are. We're not going to tell you what those functions are, but they're going to tell you some values, maybe in a table or something. So before we can, and they ask for h prime of 2. Well, before you can find h prime of 2, you need what? H prime of x. So h prime of x would equal what? What would we write it? F prime of x times g of x plus f of x times g prime of x. So h prime of 2 would simply be f prime of 2 times g of 2 plus f of 2 times g prime of 2, right? Before you can find h prime of 2, you have to find h prime of x. And the reason I say that so much all the time is because I would often have people do this. Well, if I want h prime of 2, let's first do h of 2 and then do the derivative. Well, that's silly because that'll be 0 every single time. If you first do h of 2, you're going to get a number. And then you do the derivative of that, you're going to get 0. So it's silly to think that's going to work. So h prime of 2, you can't do until you have h prime of x. And then you put the 2 in. And then what's going to happen is in the problem, they're going to either have a table of f and g and f prime and g prime values. So you'll just look up these values on your table and you'll multiply them out. Okay? Or in the directions, they'll just tell you f of 2 is 3, f prime of 2 is -1, f g of 2 is b, right? They're just going to give you these values and then you'll just plug them in and calculate an answer. Okay? So it's just another way of looking at the product rule. And same thing with the quotient rule. Okay? So you have a little bit of that. All right? And then there's going to be some problems, I think, early in the assignment where they're going to say, work it out 2 ways. Simplify it first and get the derivative, and then do the product rule. And just show that they're the same. Okay? So remember, we had done this when I was trying to prove to you, that you just can't do this, right? You just can't do the derivative of that and the derivative of that. It doesn't work. Because that would give you 6x cubed. Well, we know x cubed times x squared is what? X to the 5th. So I've done this because I'm doing it 2 ways. So I just split the screen in 2 here. It's not a T-chart or anything like we were doing earlier. I just split the screen in 2. So we know f of x is x to the 5th. So we know f prime has to be 5x to the 4th. So we know that this doesn't work, right? It just can't. So now, what would the product rule look like? Well, the product rule would say derivative of the first, 2x, leave the second one alone, plus x squared left alone, times 3x squared, the derivative of x cubed, right? And so what does that give us? Well, that gives us 2x to the 4th, plus 3x to the 4th, which of course is 5x to the 4th. And so it checks out nicely. Okay? So that's kind of gives us a good feeling that the product rule does seem to actually do what we think it would. The calculator told us that on that other one, but we kind of had to trust the calculator, which we typically would. But anyway, okay, so you're going to have some problems like that, where they're going to say simplify it first, get the derivative, or use the product rule. Now, clearly on this one, I would, if I was doing this, I would have done the left side, right? You have an option. But when they ask you to, go ahead and do that. All right? All right, so let's have some time to work here, maybe about a half hour or so on that top line. Okay? So let's work on that. Answer books are up here. If you want to check, see how you're doing, come up and ask me. That's fine too. And at about 9 o'clock, then we're going to talk about one more rule. Okay? To add to the mix here. Yes.
So it's like the last chapter that we're going to see.
Well, we might do a little bit of chapter 4. So we'll do this gateway test, and we'll probably have one small quiz before break, too. Yeah. And then we'll have a daily assignment in there, and then you got your calculus carols or calculus poems or whatever on that last day you can be thinking about doing. This rule we're going to put up right now is the most important rule of them all, because this rule just shows up all the time. And the different derivative rules get used in combination, right? So in other words, we already looked at the one where we had to do a product rule, but at the same time then, while we were doing the product rule, we did a power rule. and then like we had an x plus 4 to the fifth, and we had to remember that that plus 4, just the inside stays the same, whatever. We had that sine 3x, we had to kick out a 3, right? So to use multiple rules in a problem, but you don't have to think of it as, oh, now I got to use this rule and then use this rule. It just all kind of goes together. So here's why, the reason this is called the chain rule. The chain rule. And it's when you have a function inside of another function. Now, we've actually already seen that, because when you have sine 3x, that's a function, 3x is a function inside of the sine function, right? Now, what we've said is you just kick out a 3. Okay, well, we're going to expand on that a little bit right now. Now, the reason we kicked out the 3 is because that 3 compressed the graph, right? And so by compressing the graph, you made the slope 3 times as much, right? But we have no clue what an x cubed inside of the sine function does. It doesn't just do one thing. It depends what x is, right? And so it really changes things because you're then cubing it. When you're just multiplying by a constant, it does a constant thing. It compresses by a 3 factor. So we kick out a 3. Well, okay, Braylon, you're up again here. So let's type this in. Okay, so we're going to do sine of x cubed, and let the calculator tell us what is going on here. What happened? What did it kick out? The derivative of the inside. Now think about what we've been doing. If we have a 3x on the inside, we've been kicking out the 3. Why? Because of the compression, because I told you to. But really, isn't that the derivative of 3x, right? If there's a 3x on the inside, when we've been kicking out the 3, we've been kicking out the derivative of the inside. The derivative of 3x is 3. Well, it turns out that's what we do all the time. So if you have a function inside of another function, you do the normal derivative. Now think about this. It's really a 3-step process. You do the normal derivative of the outside function, which is cosine. You leave the inside alone. Remember, I've been telling you that. We always just leave the inside alone. So x cubed stays on the inside, and we kick out. And by kick out, we mean multiply by the derivative of the inside, which is 3x squared. So our chain rule, so the derivative of this was, now the way you usually do it is you go cosine x cubed, and then you kick out 3x squared, and then you could leave it like that, that'd be fine. But what if there was a number setting here, you'd want to put the 3. So a lot of times we rearrange it and to put this in front, right, like so. But rearranging in and of itself is not simplifying. So I don't really care about rearranging. If you just left it like that, I'd be fine. But if there was a 6 in front of that, that 6 and 3 would need to go together to make 18. Okay? So that part I would care about. That's not just rearranging. But just rearranging to be rearranging is sometimes helpful if we're going to go farther. But for the derivative test, for the gateway test, you don't need to necessarily rearrange. So either one of those would be okay. All right, so the chain rule says this. Okay? So the chain rule says, oh, and by the way, your book sometimes uses this fog, I call it fog notation. They use this open circle to mean f of g of x, right? Because that's what we have. A composition function is what we have. The chain rule is really about composition of functions, a function inside of a function. So I usually write it this way, f of g of x, but the book writes it that way sometimes. So we do the derivative of the outside, which is f prime. We leave the inside alone, which is the g of x, and then we kick out the derivative of the inside, which is the g prime. Okay, that's how you do the quotient rule. So, remember this problem a little bit ago? I'll come back to this real quick, but remember this problem a little bit ago we did? Oh, whoops, that was a different, sorry. Remember this problem here, where they gave you h of x is equal to that, and then you had to find h prime of 2? Well, in this homework, you're going to have some of the same thing. In this homework, you're going to have they're going to give you h of x equals f of g of x, and they're going to say find h prime of 2. So before you can find h prime of 2, you got to find h prime of x. Well, here would be your h prime of x right here, right? You'd write it out like this, then you'd stick your 2 in, and away you go. So then you find g of 2, put that in here, then that's on the inside of f prime, you can find some. Okay? So that's the chain rule. In words, I always say it like this. We're going to do the derivative of the outside function, we're going to leave the inside function alone, and then we're going to multiply by the derivative of the inside. Okay? Or a lot of times I say kick out the derivative of the inside, but when we kick out, we're multiplying. Okay? Well, this is a really, really commonly used rule. We don't say, oh, hey, now I'm going to do the chain rule. It's just rare that you have a function. It's just rare that we have x cubed, or e to the x, or sine x, or cosine x. It's usually something squared, or it's sine of something, or it's e raised to the something, right? It's usually some stuff inside of a function that we're dealing with, okay? So it's rarely just one of those real simple functions. So, just the chain rule gets used all the time, okay? All right, so let's go through a few examples here, and then you might have a little bit of time to keep working. Okay, so try that one real quick. Try that one. So before you get started, what is the outside function? What's the outside function? Something to the 8th. You could call it x to the 8th, but that confuses people. Sometimes they say there's no x to the 8th. Well, it's some stuff raised to the 8th power. The outside function here is the 8th power function, right? All right, go ahead and do that and see what you think. All right, so if I was attacking this, I would say, okay, I got some stuff to the 8th power. That's my outer function. But even then, you have to think about it. We've already done some stuff to the 8th power, so we know we're going to bring the 8 down in front. We're going to leave the inside alone. Now, the thing is, sometimes the inside gets so messy, but by the time you get done writing this, you forget about the 7, right? So what I often do is when I have a problem like this, I'll go 8, I'll leave the parentheses alone, and I'll do the 7, so I don't forget about it. So I'll do that sometimes. Then I'll come back and I'll stick the inside in. Okay, just a little piece of helpful advice. Times, now here's another piece of helpful advice. So I did the derivative of the outside, which is the 8 and then the 7. I left the inside alone, and now I'm going to tack on the derivative of the inside. Now, this is a part a lot of people forget, is parentheses, right? I see this all the time. I see people say, okay, now I'm going to go times the derivative of the inside. So they come in here and they go, okay, times this. Well, what's the derivative of e to the 2x? 2e to the 2x. Now, we were really using the chain rule right there, but why worry about thinking about the chain rule? We just know we kick out of 2, so just do it, right? It just complicates things if you have to think it. But that is the chain rule. Plus 3. And then people leave that as their answer. I guarantee you, somebody this year on the gateway test is going to miss that problem. That should be an easy problem on the gateway test, and they're going to miss that because they're going to write it like that. Now, what's wrong with that? Well, it needs parentheses. Why does it need parentheses? Because you're only multiplying by this thing, and you're supposed to be multiplying by all of this. And I don't care how big you make that dot, it doesn't make it any different, right? Some people do that. They put a great big dot here, like that's going to convince me that you're timesing by that whole thing. Okay, that doesn't do it. There's got to be parentheses. So when I do this problem, a lot of times I would do this. I have my e to the 2x plus 3x. That drives me nuts watching that eraser right here, but whatever. And then I would go times, and then I would put a big set of empty parentheses. I don't know how big I need, but I know I'm going to have a couple of things here, because the key is seeing that plus sign. If there wasn't a plus sign in there, right, then I wasn't going to have a plus sign out here, maybe I'd been okay. All right, so this is the answer we need, like this. There's no rearranging. You could say, well, I could take that 8 and distribute it through here. You cannot distribute an 8 through something that's got a power on it, so don't even try. So you can't do that. So just leave it. Okay, try that one. Okay, I'm going to do it here, so now don't look up if you don't want to see it yet. Okay. Now I'm just fine leaving it like that. Now some of you will be bothered by that. You want to stick that x underneath everything. That's fine. Okay, but be careful with that, because if this was, you know, say this was plus x cubed or something, right? Well, then we would have this plus 3x squared, and then you want to stick. You can't put that 1 over x. You can't put that x under all that. Right? The x could just go under this thing. So sometimes we get carried away with our simplifying and our rewriting. We do some things that are really bad. The other thing is, if I did have a plus x cubed out here, when I bring the 5 down, leave this alone, drop that to a 4, kick out the 1 over x, I got to do it right then before I move on to this. So I've got to finish doing this derivative before I move on to this. Sometimes people want to wait till the end to kick out the 1 over x. You don't do it. You do it right after you leave the inside alone, multiply by the derivative inside. Make sure you get a time sign there, right? And that stays with this term right here. Okay? Try that one. Right? Exponential functions are their own derivative. E to the x, derivative is e to the x. 2 to the x, the derivative is 2 to the x times ln 2. So we have that rule going on here, but we don't have 2 to the x, we got 2 to some stuff. We got 2 to some stuff, so you do the normal derivative. So what's the outer function here? 2 to the x, right? Or 2 to some stuff. It's an exponential function. That's the outer function. We do that derivative first. So 2 to the x, the derivative is 2 to the x times ln 2. But it's not 2 to the x, it's 2 to some stuff. The stuff is the sine x. That's the inside. The inside here is the sine x. That's the part we leave alone. So when I wrote 2 to the sine x, I was leaving the inside alone. I was doing 2 to some stuff, which the derivative of that is itself. And then leave the inside alone with sine x. I got to multiply by the derivative of the inside. The derivative of the inside is sine, or excuse me, the inside is sine, so the derivative of sine is cosine, and then I can't forget about the ln 2, right? Questions? Okay with that? Now I'm not going to let you get too far down the road here screwing this up, so I'm just going to ask you right now. What's the outer function? What's the outer function? Something squared. Very good. This is tangent of x squared. This is where I was telling, remember earlier I was telling you how this lazy notation is going to get us in trouble? This is when it gets us in trouble right here. So when you see tangent squared like that, you need to write it like I did in the red. Now do the derivative. And by the way, on page 163, the derivative of tangent is secant squared. The derivative of tangent is secant squared. Okay? Right? At its heart, this is an x squared derivative, right? This is something squared. So the derivative of something squared is you bring the 2 down in front, you leave the inside alone, you drop the power by 1, which I normally wouldn't even write, but just to emphasize what we were doing, and then the derivative of the inside, the derivative of tangent x is secant squared x. Okay? Now, could you simplify that? Not really. Tangent is sine over cosine. This is 1 over cosine squared. You can turn it into sines and cosines. Maybe see if something cancels, but it doesn't really, so it's not necessary. Okay? Okay, try that one. Again, first thing you ought to think of, matter of fact, when you write it on your paper, if it were me, I would just right away, I would write it like that. Okay, I would write it like that. Whenever I see sine squared or tangent squared or something like that, I'm writing it like that. Because it's so important now for us to know what's the outside function, what's inside, so forth, so on. What's that? Well, let's take it step by step. Let's go through it. So what's the outer function? Something squared. Then there's some stuff on the inside. Yeah, there's a bunch of stuff on the inside. Don't worry about that yet. So we're going to start by derivative of the outside. 3-step process. Derivative of the outside, leave the inside alone, do the derivative of the inside, right? It's just that that third step is going to get complicated here. So we do the derivative of the outside. That's 2 to the first. There you go. I just did the derivative of the outside, right? Leave the inside alone. Sine of x cubed. There we go. I just did the second step. Times the derivative of the inside. Third step. Derivative of the inside is going to be messy. So I made myself a great big set of parentheses because I don't know how much room I'm going to need. Right? But now I'm on the third step. So derivative of the outside I did. Write down the 2. Dropped it to a 1. Leave the inside alone, which I did. Third step, do the derivative of the inside. So now the only thing I'm looking at is the red thing now. That's all I'm looking at. So now I've got to do the derivative of that. Well, it's kind of like starting over. It's like a whole new problem, right? Because it has an outside and an inside, right? So I'm now on the third step of my chain rule, but my third step now has 3 steps of its own, right? So now I got to do the derivative of the outside, which is what? Cosine. Leave the inside alone times the derivative of the inside, which is now the green thing, 3x squared. Now, whenever I do something like that, then I step back and I look at the whole thing and I think, okay, now what can I put together? Now, what you always got to be careful of is powers on the outside. If I got like a 7 or something on the outside, I can't really do anything with this thing on the inside. Okay, necessarily. But what can I put together here? Do I need those parentheses? As it turns out, I don't, because this is times, and this is times, and this is times, and this is times. Everything's multiplied. It's like A times B times C times D. I can do it in any order. But I put the parentheses just in case there's a plus or something like that comes up in there. Okay? All right. So that's why I put it. But at the end of the day, it turns out I don't. What can I put together here that needs what I would call obvious simplifying? The what?
3 squared.
The 3 times 2, right? I need to make that a 6. Okay, so it's mostly rearranging, but I would bring the 3x squared, and I would bring that over here with the 2, and I would write 6x squared probably in front. Since this is the first power, I don't really have to worry about it. And then I got x cubed, and then I got cosine x cubed, and then turns out I don't need a bunch of those parentheses now the way it worked out. But man, I put them in there originally just in case. Okay, and there you go. And that's the final answer I'd want to see. If you had some extra parentheses in there that weren't hurting anything, that'd be okay. All right, but the 2 and the 3, you could leave the x squared over here, but I usually bring it around. Okay, but the 2 and the 3 would have to go together. That's what I would call some obvious simplifying. Okay, there you go. All right, so that's another one. We won't do this one right now, but that would be a quotient rule, right? So think about it. Derivative the outside is the cubed function. You would do that. You would leave the inside alone. And then when you go to times the derivative of the inside, big set of parentheses, and you would do the quotient rule. U prime v minus uv prime all over v squared. It'd be messy, right? It'd be messy, okay? It'd end up looking like 3 something squared. It'd just be this. This would be left alone, right? Da-da-da. And then times, and then boom. You'd have this big something, 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 minus something, 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 right? All over something squared. I mean, that's your answer would, because when you do the derivative of the inside, you're going to be doing the quotient. All right. One last, and don't you have to write this down. This is similar to something that we talked about on the other page, but they give you this function here. They say, is h increasing at 2? Well, is h increasing at 2 is like asking, is h prime positive? So what they're really wanting you to do is find h prime at 2. So it's just like that problem we just talked about earlier. They're wanting you to find, so you've got to, when you read this, you got to say h is increasing. Oh, when h prime is positive. So they want me to find h prime at 2 and see if I get a positive or a negative. So I'm going to write, before I find h prime at 2, I'm going to write h prime of x. Then I'm going to put a 2 there, and I'm going to put a 2 there. They're going to give me some numbers to plug in. I'll plug those numbers in, and if I get a positive number, I'll say yes, h is increasing at 2. See how we can use a chart there in a problem like that. Find stationary points of h would be setting this equal to 0. Set this equal to 0. When does this equal 0? When that is 0 or when that is 0, right? And we would solve those two things. Okay, we're going to work on this over the next couple of days. All right, so one last thing I will tell you on my derivative rule sheet, and I'm not going to give you this till tomorrow, but what we will do with our rules now, instead of the power rule, for example, instead of calling that x to the n, I'm going to start calling that u to the n. Okay, now why am I going to do that? Because we rarely get just x to the 5th power. We usually, as you can see now, have some stuff to the 5th power. So the u is like the stuff. The u is some function of x, just like it was on the product rule. So when I write this rule, I'm going to write it like this. So you see how I just incorporated the chain rule there, right? So this is saying our rule is, it's with respect to x now, if you have some stuff raised to the n power, you bring down the power, drop it by 1, and then you tack on the derivative of the inside, the derivative of the stuff. Okay? So all of our rules are going to be written like that. Okay, so they kind of incorporate the chain rule. So we're not going to think of the derivative of e to the x now as e to the x. We're going to say the derivative of e raised to some stuff is e raised to that stuff, and then times the derivative of that stuff, or the inside. Okay? All right. So the next set of problems, 3.2, right, you can be working on. So like I said, a little bit of leniency on getting every single one of those done, but it is, I would make sure you get into the product quotient rule problems like you've been, but also get into the chain rule side of things for a little bit on the 3.2 homework, right? And we'll have some work time tomorrow and some practice time. I'll throw some at you, let you try them, and so forth, so on. Okay?